Hello, my name is Johannes Faust, and I'm with a group of Professor Mitzos at RWTH Aachen University. And I will present DyOS, a software package for dynamic optimization using direct shooting. Together with my colleagues, I have prepared this talk. Let's have a quick look at the dynamic optimization problem first. I'm assuming that you're a little bit familiar with the topic. We have an objective function, and the most important are these two lines, which is a dynamic system, which causes the main difficulties. In direct methods, we will usually parameterize the inputs by some piecewise constant or piecewise linear function. And we then also need to solve our dynamic systems. And there are different ways. One idea is to embed a discretization ourselves into the nonlinear program or to use an external integrator. This already paves the way to the three main methods which are indirect approaches for optimal control, which is direct single shooting, direct multiple shooting, and full discretization. I will shortly cover the characteristics of each method. Let's start with direct single shooting. In direct single shooting, we have decoupled the optimization problem from the initial value problem. So the dynamics are solved with a specialized solver, a DE or ODE solver, and the results, together with sensitivities, are fed to an NLP solver, and these form a loop of iterations. In direct multiple shooting, we will split the time horizon into, let's say, independent problems and pose continuity constraints to fulfill the actual problem. In full discretization, we will discretize the dynamic systems ourselves and end up with an optimization problem which has only algebraic equations. As a general remark, we can say that direct single shooting is more suitable for very large or stiff models, while full discretization is suitable for very nonlinear or unstable systems. Let's have a look at DyOS, which stands for Dynamic Optimization Software. And it implements the two left parts, so direct single and direct multiple shooting. There are also the possibilities to solve single stage and multi-stage optimization problems. Important features of this software is that this software is open sourcely available. We have user-friendly MATLAB and Python interfaces, and we also provide different model interfaces, which are a relevant part of any dynamic optimization problem. And we have, of course, a different numerical optimizers and integrators, which are some are open source and some are commercial. And of course, we need linear and nonlinear solvers. And this C++ open source package has also a distinct feature, which is the automatic control grid adaptation, which I will focus later on. But let's start with the model interfaces first. We have three main model interfaces, which is either FMI, which stands for Functional Mockup Interface, YADE, and MADO. I will focus mostly on the FMI as it is a standardized interface and these two are developed in-house. FMI provides analytic first-order derivatives and it reduces to an ODE system and you can apply different softwares, for example, Daimler, and to get a function mockup unit which provides a function mockup interface. We use Daimler and OpenModelica, but you can use any software which provides an FMU following the standard. The other two softwares are in-house developments, which are more or less based on Modelica or into a flavor of C++ or C++ directly. In YADE, we will use source code transformation as to obtain first or higher order derivatives. And in MADO, we will use the widely used A-C operator overloading approach. Now, let's have a first glimpse into the adaptive grid refinement, so one of the key ideas of DyOS. The idea is to start with a coarse grid, so a few degrees of freedom, and adaptively refine, using wavelet analysis, this grid. So what the algorithm does is we have this procedure where we either eliminate points, so make it coarser, or refine the control. And we will then have to re-optimize with a new grid for the control. So how does it look like? Here we have plotted a control over time with a, let's say, coarse discretization. We can see it's constant here and starts growing, but this might not be a good parameterization actually. What we do then is wavelet analysis. So we will analyze the signal, and where coefficients are low, we are able to or can eliminate points, or we need to refine where the wavelet parameters are larger. We will then re-optimize with the new grid and see that we get this, let's say, little bit more refined approach. And we can repeat this and repeat and repeat until we have met some convergence, which we can define. Another possibility of DyOS is the control structure detection. We know that optimal control can have several arcs, which I will also show on this example here. So we first again optimize and assume some control structure, and then we'll analyze this result. We see, for example, that we have a time period where we have the upper bound and at the lower bound and in between the bounds. And we can reformulate this as a multi-stage optimal control problem. And then with this adaptive control, so we know we have this arc at maximum, sensitivity seeking, and at the lower bound, we can then achieve a high accuracy solution with few intervals. Let's look at the applications where DyOS has been used. It has been used for large-scale dynamic optimization, has been used for dynamic optimization under uncertainty. We have used it for integrated optimization of design and operation. And in recent times, we have used it for economic nonlinear model predictive control extensively. Now, the more tutorial-like session starts more. I want to show you or guide you through to set up an optimal control problem in DyOS and solve it. For this, we have chosen the penicillin fed batch reactor. It's a well-known reactor where we have 3 species and we have a control, a single control, the inflow of the substrate. Of course, we need some dynamic model. So we have the model equations for biomass, substrate, and our actual value product, which is the penicillin, and also a balance equation for the volume. And what we want is, we want to solve this problem. So we want to maximize the production of penicillin, here in this case at a fixed time horizon of 150 hours. Our inlet flow rate is, of course, constrained, and we have also constraints on the substrate and the biomass which have to be fulfilled. So all this together, I will guide you through how to create a functional mockup interface using Daimler, setting up our problem in Python, and call DyOS to solve the problem such that we get in the end our solution, our optimal solution, looking like this. Let's jump into the code. As I mentioned, the software is open source available. We provide the code together with the required packages on our Git page. You can clone the code, run CMake, and compile it with your compiler. If you're on Linux and Mac OS, I assume that you can do it. And for convenience, we have also provided a release with Windows binaries. You can click on these and download them. After downloading and extracting, you find all those different libraries and executables here. We also see the penicillin example we have just covered. I will open the Modelica file with Daimler and have a look into the model itself. We can see here our modeling constants, which are constant reals in this case, and the most important one, of course, for control reason, is the input, which is defined here. All controls have to be defined as inputs. We have defined 4 states. In this case, we have a simple ODE systems. We could also have a differential algebraic system. Here we have defined an output because all algebraic states have to be outputs to be accessible in DyOS. We have defined initial conditions for our differential states, and here we have our 4 nonlinear differential equations. Here we define an algebraic simple output equation. Now I want to show you how to generate a functional mockup unit. One option which is very handy if you use Daimler is to use the flag advanced generate analytic Jacobian, as this will usually speed up the integration and of course then subsequently the optimization dramatically. What we will do, we go translate to an FMU, be sure to select version 2.0 and to have the correct binaries, in this case 64-bit binaries. We can then compile the model to an FMU, to a functional mockup unit. This functional mockup unit is then compiled here. It includes the model and also the model description. I will extract it here and let's have a look. We have the binaries, which include the model files, so the equations, and a model description XML where all the variables are defined. Now let's look into our Python code. After opening the file, we see the imports first. The first import is PyDyOS, which is the Python binding for DyOS. In this file, we define the whole optimization problem, meaning the model, constraints, objective function, controls, and so on. I will guide you through. The most important part of any dynamic optimization problem is the model itself. We define it here. We say this ISO should be of type FMI, so functional mockup interface, and we define the path to this model. And the model is here, this extracted penicillin mockup unit, functional mockup unit. Then we have a single stage problem, so we'll need to define a stage. And the stage has a duration, which is fixed in this case, by saying here that it doesn't have any sensitivity. Now let's look into the control we have. The control parameter is f, and this has to be defined on a grid. And a grid is defined in this way, or can be defined in several ways. We can either simply define the number of control intervals, then we will always have an equidistant discretization, or we can define the time points ourselves and therefore provide a non-equidistant. The control can be piecewise linear or piecewise constant, and an important feature is that every control parameter can have its own grid. So you can mix piecewise constant with piecewise linear and having a fine discretization for one control and a coarse for the other one. An interesting part is also the PC resolution, which stands for path constraint resolution. Path constraints are discretized on finitely many time points, and therefore we need to make them fine enough so that we do not have violations or large violations in between. I have said that the control f needs to have a parameter which is defined here, and this parameter is of sense type full, meaning that we want to optimize it, and it is a profile. We also define bounds for this. If we want to define the initial conditions and not take them as from the model, we also need to define a parameter. The state x here, for example, could be set to 1, with an initial. This initial can also be optimized if you wish, or you can leave it as a parameter with sense no. We now have to add all the parameters we define to our stage. All in all, we have now defined the relevant parts for the integration. Now let's look into the optimization part. First of all, we need to define our objective function, which is in this case P, the amount of penicillin. And we have two constraints defined. The first constraint is the biomass, which is a path constraint, and it has to be less than 40. We could also have a different type of constraint, which would be an endpoint constraint, for example. However, in this case, we just have path constraints. There's the other constraint on the substrate S, and this is also a path constraint. We add them to our input and have therefore defined all the relevant parts for the optimization. As we have a single stage optimization problem, we will just have to add this single input. Here we define the optimization problem that we want to solve it with single shooting. We define our integrator, our optimizer, and that we want to actually maximize our objective function in contrast to minimizing. Now we define the distinctive features of adaptation here, that we want to adapt our control grid, and some integration tolerances and optimization options for the optimizer. Now we will call DyOS, result file will be penicillin result, and afterwards we can plot it. So the output is then further analyzed. So we read out the parameters and states, and then we do some plotting. But this I'll show you from the results. So I started run, DyOS is running and refining the control grid. So it starts with a coarse one and ends up with this nice solution here. You can see the biomass is increasing until it hits the bound and stays at the bound. The substrate is for the first 40 hours also at the bound, and we can see those slight variations and violations of the substrate here. If you're interested in an algorithm for more precise satisfaction of this constraint, you can read the publication of Fu and others. And we can now see also that the penicillin is then increasing nicely over time. With this, the part on the Python interface is concluded. We have also created a graphical user interface for DyOS, which is also part of the open source program. We can read in our output from our previous optimization and plot quickly the states we want to see. We can see that we can convert this also to the input back, and we can look into our grid here and see that it's not equidistantly here, and look into the optimization and all the definitions we want to look at. Let me summarize my talk. I have presented you DyOS, which is an open source tool for solving large-scale dynamic optimization problems using direct shooting approaches. It provides user-friendly interfaces to Python, MATLAB, and C++. We have interfaces to state-of-the-art NLP and DAE solvers. Its distinguished feature are the algorithms for automatic grid refinement and structure detection. If you're interested in more details, you can look at this publication. And of course, you can download our software and try it on your own. We acknowledge the funding we have received. I thank you for your attention.